Hello again, everyone, and welcome to part 2 of our lecture on chapter 6 about sampling. So, in part 1 of our lecture, we talked about the definitions of sampling, of a sample, of a population, and we really took a deep dive into the different types of non probability sampling. In part 2 of our lecture here, we're going to go into a deeper dive of the different types of probability sampling that exist. So, as just a little bit of a refresher, all types of probability sampling are defined by their use of randomization, but they vary in the methodology that is used to choose participants because that will vary based on the aim of the study. So, the key to keep in mind with probability sampling is that the idea is that there's some amount of randomization, that there's some amount of chance or equal chance that all participants will be involved in a study, but how that is almost operationalized or proceduralized will vary depending on the study of interest. So, one of the first examples of probability sampling is what we call simple random sampling. And simple random sampling is a sampling procedure that relies on the complete randomization without any specific boundaries. So every single person in the population has an equal chance of participating in the study, and there's no boundary that will exclude people or include people. Everyone has a purely equal chance. And oftentimes, simple random sampling is conducted in one step using techniques such as random number generation or drawing numbers from a fishbowl or whatever sort of technique the researcher decides, but it is a true one step procedure. And again, as I already mentioned, every single member has an equal chance of participating, and this then ensures that the sample in your study is a representation of the population of interest. And simple random sampling requires a complete list of the population from which a sample is drawn. So you need to have a clearly defined sample frame, which isn't always possible, which is why we have something called systematic random sampling, which is actually the same technique as simple random sampling, but it has a level of organization embedded in it. So it still utilizes complete randomization with some amount of organization. So, a systematic way of randomly selecting participants from a sampling frame might be used, where you have a random selection of participants from a larger population. So you have this larger population that has already been defined, and you are going to organize it in some random way, and you're going to go through that list and you're going to say, I'm going to pick every fourth participant to, or every fourth person to participate, or every second person to participate. Maybe it's every 50th person to participate. Whatever that nth number is, that is the amount of organization that you're adding to systematic random sampling. You are randomly selecting out of the entire population of interest which people will participate, but you're doing so randomly through this organization method. And this systematic random sampling approach operates under the assumption that participants are randomly ordered in a sampling frame so that everyone in the list has the same chance of participating in the study. So your sampling frame must truly be random. They can't be alphabetical or anything like that. They have to be purely random in order to determine who is going to participate based on this organization that you embed, so that every fourth person, every fifth person, every 10th person, whatever it is. But we also have what's called stratified random sampling, and this is a technique that has become valuable when a study is focused on understanding, comparing, or analyzing different groups of a population. And stratified random sampling requires an equal number of participants in each group. And each of those groups become a strata. So the strata lists the different groups to choose participants from. So within a stratified random sample, you have a population of interest that is naturally divided or maybe arbitrarily divided by groups. And your sample is going to be stratified in a way that matches the way that it is stratified in the population. And each of those groups that is created becomes its own strata. So a good example of this might be if you are doing research comparing across sex assigned at birth, you might have a strata for each category of sex assigned at birth, and then you can draw those comparisons to analyze the differences in those groups on whatever your construct of interest is. We have two different types of stratified random sampling. The first of those is proportionate stratified sampling, which is the type of sampling that follows the proportions of the population, but also creates specific strata that are of interest to the study. So if you're looking at a true proportion of however many people in the United States are assigned female at birth, however many are assigned male at birth, and however many are assigned intersex at birth, you are going to use those exact same proportions of people in the United States to your sample population, to your samples of participants, so that you have the exact same proportions. We also have disproportionate stratified sampling, which is a sample in which the proportions are not equivalent to the proportions in the entire population. A good example of this is if we are wanting to draw meaningful differences in conclusions across groups, but in our society the groups are clearly overweighted in one direction, we might do disproportionate stratified sampling so that the strata are of proportionate sizes to each other, even though they don't represent what's in the population. So a good example of this is if I want to look at the differences in individuals who are assigned intersex at birth and their experiences with suicide and compare them to individuals who are assigned female at birth experiencing suicidal ideations. In our population, the amount of people who are identified as being assigned intersex at birth is less than 1%. But in my study, I want to draw meaningful conclusions across these groups. So I'm going to draw fewer people who are assigned female at birth in proportion to our society, but I'm going to pull the same number of individuals that I have for intersex so that I can draw meaningful conclusions. So here's a little bit of a breakdown to help with this. So in proportionate strata sampling or proportionate stratified sampling, our strata are exactly divisions or like categorizations of our population. So we're taking, okay, here are all of these different types of shapes that are in our population. Here they are broken up into their natural groups. And to get my sample of a much smaller size, I'm going to have the exact same proportions because they are all equal. They will all be equal over here. In disproportionate sampling, we see that there can be this weight where it doesn't represent, our sample doesn't represent not what's in the strata, nor does it represent what's in the population, but this might provide us with the numbers that we need to draw meaningful conclusions across our groups. Within probability sampling, we also have what's called cluster random sampling. And this is a useful technique when the population of interest is widely spread out. So when a researcher wants to use cluster random sampling, they have to follow two steps. First, they have to have clusters that are randomly defined. And a cluster in this case is a group of a population in a specific geographical region. And then participants are then randomly selected from each participating cluster. And cluster random sampling as a whole tends to be really helpful in educational research because oftentimes educational research is spread across entire nations. So you might say, as an example of cluster random sampling, that I'm conducting a study on different education standards for algebra across the United States. And I want to know what it is across the entire United States. So I might create a cluster that breaks down all of the different schools because there are so many schools and it would be impossible for me as a researcher to collect data from every single school. So I might create a cluster that says each cluster is defined by its geographical region. So I'm going to have 50 clusters, one for each state in the United States. And this is excluding territories just for this example, just for simplifying it. So I'm going to have 50 clusters. And then within each of those clusters, I'm going to randomly select the number of people who will participate from each cluster. So I'm going to have 100,000 from Colorado, 100,000 from Texas, 100,000 from California, whatever it is, I'm going to then randomly select the number from each cluster after I have created the clusters. And then from those clusters, I can draw meaningful conclusions. So finally, I want to talk a little bit about sampling assessments and sort of some characteristics that come up in the ways that we assess if our sampling is accurate. Because after you've conducted a sample or you have collected a sample of people to participate in your study, you need to know that the sample that you selected is good or not. And one of the ways that we do that is through sampling error. And sampling error is a statistical measurement that broadly represents how different the sample size in our study is from the population of interest to us. We use sampling error almost exclusively in quantitative studies, and we use it primarily to help us determine whether our sample is sufficiently representative to the entire population. So sampling error is a way for us to say whether or not our research sample matches the population adequately enough. And if it does, then we can move forward with our sample. If it does not, we have some amount of error that needs to be corrected. Small sampling size indicates a good match between the sample and the entire population, which allows researchers to sort of determine or generalize their findings beyond the sample. So you want a small sample size that is a good match to our population. The problem is that sampling error is measured for different parameters of the population that are the focus of the study. So you can determine your sampling error dependent on which part of the study is of interest to you, which sort of characteristic of the population is being reflected in your sample, which will then give you an even more robust sort of determination of what is going to be the best representation in your sample. We also have what's called confidence intervals, and these measure the confidence or lack of confidence that we have in our sample size and our sampling method. A confidence interval is one of the first indexes that is looked at in a quantitative study, because the confidence interval tells us with an amount of confidence gives us an amount of confidence that we can have that our results are accurate based on the population of interest and based on the sample that we collected. And in general, higher confidence intervals or higher sample sizes will lead to higher confidence intervals. So you want a larger sample to get a better confidence interval and a more stable confidence interval. And then because both confidence intervals and sampling errors are more specific to quantitative studies, I also want to talk to you a little bit about qualitative sampling assessment. And we primarily use the term saturation. And saturation is a measure that's used to estimate the right sample size in qualitative work. And saturation refers to the amount in qualitative data collection where no new information is coming in during data collection. So we say that someone has reached saturation in a qualitative study when they are interviewing a new person and they are no longer getting new information. All the information that they're hearing from those people is something that they've already heard from previous participants. When you have reached saturation, no new information is coming in, that means that your sample size is sufficient and you should stop data collection. So we use saturation as an assessment of our sampling method as well as our sample size. So that is where we are going to wrap up our lecture for Chapter 6. Make sure that you're reaching out and doing work on the Chapter 3 submission and reaching out if you have questions. I will see you all in the next lecture.